Any object moving in two dimensions has a horizontal and a vertical component. Each can be graphed separately against time. Here, the vertical position is constant, while the horizontal is sinusoidal. We could run the same animation with a vertical position that is cubic sinusoidal. But I don't know of any objects that actually move like this. So maybe we want to animate something realistic instead, like a bouncy ball. This can be done using a combination of exponential decay, absolute value, and the sine function. Finally, we can add one more touch of realism by making its horizontal position linear. Stick around and I will teach you how you can design your own motion functions in Desmos. Open up the Desmos graphing calculator. And here at the top right, you'll find the graph settings. So this is where you can turn on the reverse contrast if you want. You can make it small text, large text. I'm going to go large here for the tutorial. And then, okay, a few other things. If you've moved your graph around, this home icon will appear. That's the default viewport. If you press that, it'll snap the x-axis between -10 and 10, regardless of how zoomed in you are. Now, I'm going to go ahead and move this so that my y-axis also ranges from -10 to 10. Now, I'm just telling you these things because the numbers that I use moving forward will all revolve around the fact that I'm using a range of -10 to 10 on the x and the y-axis. So again, you don't have to do that. That's just for this tutorial. So good. The first thing I want you to do here up top is type T0, T sub 0. It will automatically make it a subscript. We're going to let this equal 0. Then you'll have the option to fill out the range here. Again, we're going to go from 0, but the upper boundary I want to be 8. I'll explain why momentarily. The step is going to be 0.001. The smaller the step, the smoother the animation. So it's somewhat analogous to a frame rate. Good, and then let's go to animation properties here. We're going to play this once in the forward direction. Now, Desmos is designed so that when the speed is 1x, the slider takes 4 seconds to play. Meaning, if we bump that down to half speed, the slider will take 8 seconds to play. And that's why I typed in from 0 to 8. Now, you could type in from 0 to 1 and normalize everything, but the slider would still take 8 seconds to play. So for consistency, I like to put 8. But again, you do what you want. Good. Now, I have all of these functions and my object organized in folders. So to add a folder, you hit this add item button, and then there's your folder option right there. So you don't have to do that. It's just a way to keep things organized. So the first function we're going to type out is the linear function. Now you've all heard of y equals mx plus b. That's what we're using. Instead of an x though, I'm going to use t for time, our independent variable. Now, good. I named this function h of t. Right? That's because our horizontal position is going to depend upon this function. Now again, to be consistent with my scale of -10 to 10, I'm going to go ahead and start at -8. My b is -8. My object is going to start at -8. And then I'm going to let my slope be 2, meaning 8 seconds later, it'll be at +8. So again, you do what you want, but that's what I'm going to use for this video. Good. Our next function is going to be the sinusoidal function. Now, I titled this V of t because this is going to control the vertical position of our animated object. Now, we'll change this to other functions later, but we'll start here. A stands for amplitude. I went ahead and went with 8. B here controls the period. It's related to the period. If you let B be pi, the period will be 2, a nice whole number. Good. C here controls the horizontal position, and I'm just going to go with 0 to keep things nice and centered, and D controls the vertical displacement, or the initial value, but I'm going to go with 0 just, again, for simplicity. Good. After that, we have the cubic sinusoidal. Now, this is exactly the same as the sinusoidal, except make sure you wrap the sine part in parentheses and cubic, and cube it. You could square it, fifth power, square root, whatever. I'm going with cubic for this tutorial. Now, you don't want to use the same letters. The same letters? Yes. You don't want to use the same letters twice. So I've already used A, B, C, and D. Here we're going to use W, X, Y, and Z, but they control the same thing. So I'm going to go with an amplitude of 8. a period of 2, which happens when x equals pi, and then a horizontal and vertical shift of 0 to keep things nice and centered. Now note here that I just called this function f of t. I've already used h, I've already used v, and we're going to move those around. But for now, this is just going to be a generic f for function. You can use whatever you want, really. And then the last function I used is that function to bounce, to create the bouncing simulation. So here's that. I used different letters than I used in the demonstration. It's all arbitrary. If you want to use alpha and beta, you have to type out ALPHA for alpha and BETA for beta. Other than pi, those are the only 2 Greek letters that I found that Desmos will recognize. And these are the values that I'm going to use. Honestly, I don't really know what these do. Well, M is like an amplitude in a sense. I guess N is related to, it's probably called the decay factor. But anyways, it'll work. You can move those around, play around, see how these change the function. All right. And I titled this another just f of t, generic function for now. Good. All right. The last thing we need is an actual object to animate. So just like in the demonstration here, I have the circle. I went ahead and added the center of the circle just for reference, but you do what you want. So those are those. All right, good. Everything's ready to go now. Remember, we went ahead and set the horizontal position dependent upon the linear function and the vertical dependent upon the sinusoidal. So if we hit play, that's what's going to happen first. It's going to move from left to right linearly, and then its vertical position is going to be sinusoidal. And then the animation lasts 8 seconds, and there's the end of it. Good. What about the other functions? So let's go ahead and back this up to 0. We're going to go to the sinusoidal function where we left our v. We're going to delete that v and replace it with an f. Notice your object disappears. That's because we haven't defined v anywhere. It doesn't really know what to do vertically. But we're going to go to our cubic sinusoidal function and replace the f with a v. So now the cubic sinusoidal function is going to control the vertical displacement. Hitting play. Here we go. Horizontal is still linear, left to right, but we can see that vertical position following the cubic sinusoidal. Good. All right, back that up to 0. And you could probably predict what we're going to do. Go to the cubic sinusoidal, remove the v, put back the f. Go to your bounce function and replace the f with a v. Our object comes back. And here we go. Now it's going to bounce. It's going to go out of screen here because my amplitude was larger than 10. But here we go. It bounces to the end. Obviously, this is not following, physics on Earth. But, you can play around with this. Let it be whatever you want it to be. Now, throughout the tutorial, I kept the horizontal position dependent upon the linear function. You can change that. You don't have to use any of these functions. You can use whatever you want. In fact, I encourage you, get creative with this. It can be as unrealistic or as realistic as you want it to be. Most of the things in this video were arbitrary, right? The numbers that I used, the values that I used, the functions that I use, you can do whatever you want, right? But anyways, hope you learned something. Thank you for sticking around. Please like and subscribe, and we'll see you in the next one.